Hello everyone. We are solving question 55 of GATE 2018 chemical engineering paper and the subject is heat transfer. The question is a hot liquid is to be cooled in a 1-1 cell and tube heat exchanger from 80 to 50 degrees Celsius. Cooling water enters the tube side at 30 degrees Celsius and exits at 45 degrees Celsius. The properties of liquids are constant. Also, the overall heat transfer coefficient is same for countercurrent and co-current modes. The percentage saving in heat transfer area for countercurrent option with respect to the area of co-current option is less. So for the given shell and tube heat exchanger, we have been asked to compare the performance of this countercurrent as well as co-current mode. So for a general schematic of any shell and tube heat exchanger will be like this. Let's say we are having multiple tubes. So from here my shell side fluid will enter. And it will get T in minus T out, and from here my tube side flow will enter and it will get out. So now if the in this the direction of both the cell side fluid and tube side fluid is this, so this is my co-current flow, and if I introduce this shell side from over here and bring it out from over here, then the flow direction will be opposite and that will become my counter current flow. So for both of these cases we can draw the temperature profile as, let's just write this co-current flows. So along the length of the heat exchanger, so the hot liquid, the temperature of the hot fluid will decrease from 80 to 50 degrees Celsius, and the cooling water enters the tube side. So for tube side it will increase from 30 till 45 degrees Celsius. The flow directions are same. Similarly for counter current, we can draw the profile as, the direction of will be opposite, so the temperature of the hot fluid will decrease from 80 degrees Celsius to 50 degrees Celsius. The temperature of the cold fluid will increase from 30 degrees Celsius to 45 degrees Celsius, and direction will be opposite to the first one. So for both of these fluid, the heat exchange, the usually from the energy balance we can write that Q is given as UA delta T LMTD, and this will be become QH, that is heat exchange by the cold fluid, or the QC, where QH is, you can write it as MCP of hot fluid into delta T. For cold fluid you can similarly write it as MCP of cold fluid into delta T. So ultimately we have to calculate this log mean temperature difference and then equate all this equation. And log mean temperature difference is defined as delta T1 minus delta T2 upon ln of delta T1 upon delta T2. So the log mean temperature difference for co-current flow, we will find it as delta T CO is, here delta T1 is 80 minus 30 is 50. It is delta T1 is equal to 50 and delta T2 will become 5. So we can write this log mean temperature difference for co-current flow as 50 minus 5 on ln of 50 by 5. This we can write it as 45 upon ln of 10 302, and this will become 19.54 degrees Celsius. Similarly, for counter current flow, we can write it as, here your delta T is 20 degrees Celsius, and on this side delta T2 will become 35 degrees Celsius. So we can write this as 20 minus 35 on ln of 20 upon 35. So this will become minus 15 minus of 0.5596. This will come around 26.804 degrees Celsius. So for both of this co-current and counter current flow, we are having log mean temperature difference. And now we can write this as, we know that U UA delta T LMTD for, let's say, co-current flow will be equal to mass flow rate of cold fluid, Cp of cold fluid, into the temperature difference of the cold fluid. So here delta T for the cold fluid will be 45 minus 30. Similarly, for the hot fluid, we can write this as delta TH delta TC. Here delta TH will be 80 minus 50. Now similarly, for the co-current flow, for the counter current flow, we can write it as UA LMTD upon CC is equal to, now the heat exchange will remain same as the counter current flow because the mass flow rate is same, Cp will remain same, and delta Tc, that is the temperature difference of the cold fluid, will be same as the previous one. So ultimately this term is equal to this term, and this hot term will be equal to this term, and we can take the ratio of this equation and we can write it as UA delta TLMTD co-current flow upon UA delta T upon counter current flow. So ultimately these two terms will remain same, that this will become 1. And from the question, we have been given the overall heat transfer coefficient is same for counter current and co-current mode. So this U will also get cancelled. And let's just call the area for counter current flow as ACO, and for area for co-current flow as ACO, and area for counter current flow as ACC. So this will be equal to delta T LMTD for counter current flow, and this will become LMTD for co-current flow. Okay. So this we can write it as delta T for counter current flow was given as 26.804 upon, for co-current flow it was 19.54. So we can calculate this and it will become 1.37. So ultimately we are having area for co-current flow upon area of counter current flow as 1.37. Now we have been asked to find the percentage saving in heat transfer area for counter current option with respect to the area of co-current option. So that is, we have been asked to find ACO minus ACC upon ACO. So this will be equal to 1 minus of ACC upon ACO, This we can calculate it as, this will come around 0.271. So ultimately in percentage, the savings can be written as 27.1%. So yes, so if the mode of the flow is counter current, then we will observe 27.1% saving with respect to that of co-current flow. That is why we can go ahead with counter current option, as it will what we will be saving on the heat transfer area. Yes, the final answer we will report it as 27.1.